We now know that clocks that are in sync from the perspective of one set of observers are not in sync from the perspective of another set of observers moving relative to them. And we're going to make use of this asynchronous nature of clocks in motion to carry out the goal that we have set for ourselves, which is to have a nice systematic dictionary, a mathematical formula from the coordinate system of those in the platform to the coordinate system of those in the train, including in that coordinate system the clocks of each set of observers. That's where we're ultimately heading. But before we do that, I thought it would be kind of fun to take a moment out from that task and just look at the way in which we can use this realization of asynchronous clocks to understand some of the things that we have already encountered, and to use it to come to some pretty surprising conclusions about some things that we've yet to discuss. Okay, so the first example that I'd like to look at is the issue of length contraction, but now viewed from a different perspective, right? So when we initially spoke about length contraction, what do we do? Let's think about it again, reflect back. So we had Gracie on the platform. George is rushing by on a train, and she seeks to measure the length of his train by using a watch, right? So when the front of his train passes, she starts the watch. When the back passes, she stops the watch. What does she do with that duration of time? Well, she multiplies it by the speed of the train to get the length of the train. Velocity times time is the length. And we concluded that that number would be smaller than the number that George, who's on the train, claims to be its length. And we understand that because her clock is ticking slow from George's perspective, so she gets a smaller length. That all makes good sense. But here's the thing. Using our coordinate system that we've now spent some effort setting up, there's another way that Gracie and her team of friends in Team Platform can measure the length of George's train. And this particular way that I'll now show you doesn't seem to make use of the rate at which time elapses on her clock at all. So I'll show you the video in a moment. Let me just quickly tell you what you're going to see. Right. So Gracie's new approach is this. She has set things up with the engineer of the train in which George and his compatriots are moving. She set it up so that the front of the train is going to pass by her at exactly 12 noon. Let me do it this way. So the train is going to come in, and at exactly 12 noon, she set it up so that the front will pass her. She says to all of her friends that are flanking her on left and right, she says, when the back of the train passes you, look at your watch. If your watch also says 12 o'clock, raise your hands. Why? Because since Gracie's measuring where the front of the train is at 12 o'clock, it's right where she is. If she knows where the back of the train is at 12 o'clock, and she'll know that by looking at her friend whose hands go up, she'll just measure the distance between her and her friend, and in that way, she will measure the length of the train. Okay, let's see that in action. So here it is. We've got the train coming in to the station. Oh, it's coming from this side. So it's set up so that 12 noon, it just passes Gracie. She puts her hands up, and it's this person over here. It's this member of her team who found that the back of the train was passing her at 12 noon, and all Gracie then needs to do is look at the length between her and her friend. So again, just so you can see this in a little bit more detail as we're going to analyze this, the train is coming in. She has already set it up so that at 12 noon, it's all worked out. It is just passing her. She puts up her hands. Her friend down the line is waiting for the back of the train to pass, looks at her watch. It's also 12 noon, so she raises her hand, and it's the distance between the two that they will now claim is the length of the train. And the reason why I'm describing this alternate approach to measuring the length of a train is because in that scenario, the rate of time that elapses on Gracie's clock seems irrelevant, right? We haven't had any time elapse on her clock at all, really. We just set one moment in time when the front of the train was passing her. So the question is, since the rate at which time ticks on Gracie's clock and her friend's clock seems not to matter, how do George and Team Train now explain the fact that Gracie and her team get a shorter length for the train than he and his team do? Let's work out the claim that they make now to explain the discrepancy in the lengths. Here's how it goes. It makes use of course, the asynchronous clocks. So what George and Team Train claim is that the clocks in Gracie's frame, in Team Platform, they claim those are not in sync because from Team Train's perspective, the platform is moving, right? And in a little bit more detail, they claim that Gracie's clock, right? They say that Gracie's clock is ahead of her friend's clock. Why? From the perspective of Team Train, right? Team Train, when we saw the animation, was coming in this direction, right? Which means from the perspective of Team Train itself, the platform is moving that way, right? If the platform is moving that way, we know that clocks that are in the rear of the motion are ahead. Gracie would be in the rear. She's in that direction relative to her friend. So Gracie's clock, according to this reasoning, would strike 12 noon before her friend's clock did. What does that mean? Well, the location of the front of the train is measured first. The train continues to move, and only then is the location of the back of the train measured. So according to Team Train, it's obvious why Team Platform gets a shorter result. They measure the location of the rear of the train after it has moved forward. So let me show you what that then would look like in a little animation over here. So now we are in George's and Team Train's perspective, okay? Coming into the station, there's the platform. They claim that Gracie throws up her hands first, and then her friend throws up her hands, thereby measuring a shorter length. Let me show you that in a little more detail. That went by a little fast. So here we go. Going to watch it slow down a bit, and we'll put some stops in the middle. George is coming in. 12 noon, Gracie throws up her hands. Okay? Now, I want you to focus on the clocks. Let me make them a little bit more visible. So I've made the second hand longer so you can see it. Notice that the clocks going this way are ever further back, right? They are ever late. That's the asynchronous nature of the clocks. So from George's perspective, the clocks to the right have yet to reach 12 noon. So it's only later on, when there's enough time elapsed for these clocks to go forward, that Gracie's friend, her clock will finally reach 12 noon. But in the interim, the train, of course, has moved, and therefore they will get a shorter length. They're only measuring that piece of the train because the train is moving. So if we now take a look at this in full glory, George and his train, they are coming in, and they find that Gracie throws up her hands first, her friend throws up her hands second, and in that way measure a shorter length for the train. So it's a nice application of this asynchronous nature of clocks. Now we have another way of thinking about length contraction that all has to do with one set of observers not agreeing on what the other set says are clocks that they claim are in sync. The other set of observers say that they are not.